All right, now in order to understand how vesicles get filled with neurotransmitter, we have to go back and look a little bit at the driving force that's going to move them across those membranes. So we're going to go back and review the electrochemical potential mu, which is defined as some baseline state mu0 plus the gas constant times absolute temperature times the log of a concentration of a charged ion plus an electrical potential that's dependent on the valence of the charged ion and the Faraday. This mu0, this electrochemical potential, is some ground reference state. And if we have a two-compartment system, the inside and outside of a cell, one can calculate the mu sub A for the inside or the mu sub B for the outside, and also the difference between them. What's the difference in electrochemical potential across that membrane? And we do that by subtracting one from the other and substituting the top equation into that equation and simplifying, basically come up with a term for the net or difference electrochemical potential across that membrane as proportional to the log of the concentration difference. So there's a concentration term plus a potential, electrical potential difference times the valence and the Faraday. So this quantity delta mu represents the extent to which the concentration gradient across this membrane or across these two compartments is removed from an equilibrium situation. Now, one can continue with these equations and actually derive the Nernst equation, and I do that for you in the summary and reference material that I have posted on the website for today's lecture. All right, so when we take delta mu on a molar basis and divide it by the Faraday, we get the Gibbs free energy change of the system, which would be an overall driving force acting on the ions in question. For a synaptic vesicle, since hydrogen is clearly our dominant ion here, and true of other organelles, we call this delta mu sub H, and just substituting hydrogen and pH into it, we have delta mu sub H has an electrical term and a pH term. So by going from the natural log to the log base 10, we pick up at 2.3, and we simplify. So we have an electrical term which is now called delta psi, and all of these constants are approximately 60 times the change in pH difference across the membrane. So this driving force has two terms, an electrical term and a pH term. We are not at equilibrium, so they do not equal zero. There is some value to delta mu H. And one has to consider both of these driving force components when looking at the behavior of ions and molecules within the vesicles. The high intracellular hydrogen ion concentration accompanies a positive intracellular electrical potential relative to the cytosol. So here we're assuming the cytosol is, quote, 0, and this inside of the vesicle is 50 millivolts higher than the cytosol. This is not relative to the extracellular space, it's relative to the cytosol. So we're looking only across the cytosol to the vesicular interior. High positive interior essentially is sufficient to repel sodium and potassium, and that accounts for the very low concentration of sodium and potassium that we saw inside the chromaffin granules from the biochemical analysis. Now, the high hydrogen ion concentration clearly is attracting chloride as a negative ion to counterbalance that, both for charge balance and for osmotic reasons. And as chloride comes into the cell, it also can bring hydrogen with it. But as it does, it would, for charge balance, decrease delta psi, but it will increase delta pH, and therefore the overall electrochemical potential would not change with more chloride entry. But chloride becomes a very important counterbalancing ion. If in an isolated synaptic vesicle or granule preparation, high extra granule chloride were applied, that could cause the vesicles to swell. All right, so we've got these two components of the driving force, delta psi and delta pH, and it turns out different vesicular neurotransmitter transporters utilize one or the other or both of these in their efforts to load neurotransmitter into the vesicles. If we look at the glutamate, the vesicular glutamate transporter, this V-glut utilizes the electrochemical potential, the electrical part of this, delta psi, much more than it does the pH gradient. Cytosolic glutamate is 10 millimolar. We're looking at vesicular glutamate in the 150 millimolar range. So there's not a large concentration gradient to move against, but the charge difference, because glutamate itself has a negative charge at physiological pH, is very useful for getting glutamate into the cell, into the vesicle. On the other hand, the vesicular monoamine transporter utilizes the pH component much more than it does the delta psi component. And that's because the large hydrogen ion concentration inside the vesicle also acts to eliminate weak acids, but to attract weak bases into the vesicular lumen. So any kind of an amine, even ammonia, which would cross this membrane in the neutral form and get into the vesicle and then become protonated. And once it's protonated in the NH4 form, it can't leave, it gets stuck. So that's part of how the monoamines accumulate to such a high concentration inside the vesicle. Because all of them, dopamine, norepi, and epinephrine, all are amines. Serotonin the same way. They have an amine terminal, which essentially traps them inside the vesicle. The glutamate, or not the glutamate, excuse me, the GABA transporter, on the other hand, utilizes both delta psi and delta pH approximately evenly, and depends on both of those driving forces in order to move GABA up a concentration gradient and into the vesicle. So do biochemists measure the same kinds of concentrations inside synaptic vesicles that we saw in the Bruns and Jan experiment that we read on Friday? The answer is absolutely. These are numbers from biochemical extraction of transmitter out of purified vesicles from the torpedo electric organ, from more chromaffin cells, from dense core vesicles in pig platelets, in insuloma cells, and you can see very high concentrations not only of the transmitter itself, but also of nucleotides, ATP. So very comparable high concentrations of those and calcium. So very consistent across all kinds of secretory vesicles.